Hello, this is Tom Hobbs, and this is the fourth in our series of videos on Bayesian tools for synthesis of ecological data. The topic for this discussion is how we analyze data from multiple studies. The overarching objective is to learn Bayesian methods for bringing together data from diverse sources, as well as published findings and statistics, to enhance our insight in ecology, to enhance the findings from our own individual research studies. It's a video sequence. In video one, we reviewed the concept, the components of Bayesian inference. We talked about why we would want to use informed priors. And we posed a problem, how we use published means and standard deviations, which are usually the substance of tables in published work. Given that means and standard deviations are not the parameters of most statistical distributions. In video two, we proposed a solution to that problem, moment matching, a very useful technique. Then we went on to develop show methods for informing priors from multiple studies, multiple published studies. And now we're going to talk about hierarchical or multi-level analysis of data from multiple sets, from multiple studies. Slides for this lecture can be found at my GitHub site. And also at that site, you will find a worked problem, a worked series of problems, actually, that deal with the material presented in this lecture in some detail and allow you to actually try out these techniques. There's both math and coding in this exercise, and I recommend that you follow up this video by doing the exercise. It's quite substantial. So the problem that we dealt with in the previous video was combining published results from multiple studies. Really, how do we combine published statistics to inform prior distributions? And today we're going to assume we actually have the data sets, not published statistics, but complete data sets from multiple studies that have the same response and at least some shared set of predictor variables. So we're going to discuss how we use Bayesian methods to build up a comprehensive analysis using data sets collected at different times in different places. So the example we're going to use is a regression model reflecting data from CapJ number of studies. So I've illustrated those different data sets with separate spreadsheets here, and they must have a shared response, and they must have at least some shared predictor variables. So what are the alternatives to analyzing data sets like this? Well, the first one is we could pool everything. We could simply pretend that these data are not from different studies, throw them all into the same spreadsheet, and analyze them as if they were a single study. That might be convenient, but it's statistically indefensible. On the other hand, we could take each spreadsheet and analyze each sub-study separately, but that's pretty much a waste of time because that's already been done. Presumably, or even if it hasn't been done, we might end up with 15 different regression models. And so it's pretty hard to draw new shared insight across those 15 different model fits. The alternative that we're going to learn today is how to analyze the studies hierarchically, an approach that's also called partial pooling or multi-level modeling. It's the statistically reliable approach to combining data across studies. So the hierarchical approach is diagrammed here, illustrating how we can model the intercept as being drawn from a distribution of studies. So in the directed acyclic graph at the top here, we have the ith response in the jth study. We say that those responses are drawn from a model with a shared intercept. So each each study has its own intercept, alpha j. There are common slopes across all of the studies, and there's a variance term. The important idea here is that the intercepts, alpha j, are drawn from a distribution of intercepts. And I have the corresponding posterior distribution and its proportionality to the fully factored joint distribution for a simple regression model with a cap j number of studies. So what we really want to understand is the statistical distribution of the intercepts. That's how we're going to gain insight across all of the studies. So in the left-hand panel, the different colored symbols represent different studies. We're assuming they all have the same slope, but we'll relax that assumption a little later. And we want to know what's the distribution from which the intercepts of these different models were drawn, and that's shown in the right-hand panel. A great advantage of this approach is called borrowing strength. And so I have a directed acyclic graph here for a hierarchical model, and we're just going to focus on the mean intercepts as if all of the predictor variables had been standardized. So, and we're making inference at the mean of the predictor variable. So alpha 1 through alpha j are just the intercepts, or they're the means. The data are vectors from study 1 through study j. So each y there represents a 1 to n sub j number of observations in study j. And notice that the intercepts, the alphas, are drawn from a distribution with mean mu and variance sigma squared sub alpha. So here's the model for those intercepts, again, assuming that the slopes have dropped out because we're interested at the intercept at the mean of the predictor variables. So we've got the data model, and we've got a model of the process, and then we've got priors on all the parameters in our model. Now, this illustrates borrowing strength, the inference we can make beautifully. So it's a little bit of a complicated graph, so let me show you around. On the x-axis, I've got the study number, so it's actually j. So j goes from 1 through 20. And just for convenience of plotting, the study number or the study index j corresponds to the sample size, the number of observations for the regression model within study j. And then the crosses on here are data that have been simulated. So those are known. Those are the true values. And we have two different models, no pooling, as if each study stood alone. We didn't draw on a shared distribution of intercepts. And then we have partial pooling. We're assuming that the intercepts are drawn from a distribution. And look what happens. As the sample size increases, the two things happen. The studies with small numbers of observation get pulled toward the overall mean. But not only that, we see substantial shrinkage in their variance. So this is what's called borrowing strength. Studies that are done with small sample sizes or with high amounts of data error get pulled toward the overall mean with a shrinkage in variance. Now, you may have heard these models, you probably actually have heard these models called random effect models. So we have a mean for the ith observation in the J study that's predicted by our regression model, where we have a zero-centered, normally distributed random error that's added to that model. And then the yij's are simply the mu ij's and some sigma squared. Notice that that's absolutely algebraically equivalent to saying that each study has its own intercept. It's rather than having an intercept across all studies where we add an error term, we simply allow each study to have its own intercept. And those intercepts are drawn from a distribution with an overall mean and a variance var sigma squared. These are absolutely identical, and I prefer the second for a couple of reasons. It's pretty well known that the term random effects is used in a whole variety of ways, sometimes somewhat contradictory ways. So random effects and fixed effects can be quite confusing, and we eliminate that confusion by using the multi-level model in the on the lower part of the slide. The other reason that this is important is that the upper model, the traditional random effects model, depends on additive errors. And there are models for which errors are not additive. For example, for random variables that have to be strictly positive. I'm going to focus on models that use the form below, but you should know that these are algebraically equivalent to the random effects approach. So what if we happen to have data, not only data within individual studies, so X's and Y's within study 1, study 2, and study 3, but we also have data on the studies themselves. So we might have a covariate for each one of the studies. That allows us to model the intercepts as a function of those study level covariates. So we can model the intercept, or the slope for that matter, as a function of study level data, as shown in this directed acyclic graph and the corresponding posterior distribution and its relationship to the fully factored joint distribution. Well, that's all fine and good, but often we're not going to want to only model the intercept, but rather we're going to model the intercepts and the slopes across several studies. And that requires modeling the covariance. So imagine that we've got a vector of 3 random variables, Z1, Z2, and Z3. The covariance between any 2 of these random variables is simply an unstandardized version of the correlation between them. It's the correlation measured in units of the random variables. The covariance matrix is then shown here. On the diagonal are the variances, and on the off diagonal, symmetrically, is the covariance, which is equal to the covariance between random variable I and random variable J, which is equal to the correlation coefficient multiplied by the standard deviation of random variable I and the standard deviation of random variable J. This could take on values between -1 and 1, but covariance can take on values between -infinity and +infinity. So to illustrate here, let's imagine that we have cap J number of groups with multiple observations within groups, and we fit a 2-parameter linear model to each group, that is one with an intercept and a slope. So we find cap J intercepts and slope, 1 for each of the J studies. We're going to denote the vector of intercepts as bold alpha and the vector of slopes as bold beta. So we can calculate the variance for each of those vectors and then the correlation between them as rho. The variance covariance matrix is thus the variances on the diagonal and the symmetric, covariances symmetrically on the off diagonal. So to model the intercepts and slopes, the directed acyclic graph is shown in the upper part of the slide. We have a vector of alpha j, beta j. So the intercept and the slope for study j is going to be distributed multivariate normal with the first parameter a vector of mu, the vector of means of the intercepts and slopes of the intercepts, and the covariance matrix. And this is what our, for that case, for J studies and models with intercept and slope varying across studies. This is the fully factored joint distribution and its relationship to the posterior. Now, what if we have intercepts and slopes for more than one slope? Well, so if we have m slopes in our model so that the coefficients go from beta 0 to beta sub m, we simply have a larger vector. We have a larger vector of coefficients in the model, but otherwise the model is precisely the same. Now, how do we set priors on the covariance matrix? There's a pretty easy way to do that using the Wishart distribution. And we say the prior on sigma, a flat prior on sigma, a vague prior on sigma, is sigma distributed Wishart cap S and m plus 1, where S is an m by m matrix with ones on the diagonal and zeros on the off diagonals. And m is the number of coefficients in the model. If we want the variances and the correlation coefficients, then we can compute those as derived quantities of the element of sigma if we include those derived quantities in our JAGS code. But we do need to remember that sigma in JAGS and in OpenBugs uses precisions, not variances. So those have to be transformed. I have some guidance on this based on experience. The Wishart is an easy, useful way to impose reasonably vague priors on covariance matrix. Gelman and Hill, 2 pages, let's see, that's the Gelman and Hill book on multi-level modeling, pages 376 to 380, has a description of how to use the Wishart. But my experience is that these priors are vague for the means, but they're somewhat informative for the variances and for the correlations. The RJAGS GLM module has a scaled Wishart that seems to work somewhat better, and I give you some references for how to do that. It's also entirely feasible, if tedious, to expand that 2-parameter case that I showed you earlier to include more than one slope. So I now want to just talk about a little bit of coding, because it's a really essential trick for implementing these multi-level models. So presume we've got, again, CapJ studies. Our data are in spreadsheets with rows and columns, and we have data on each individual study. So the question is, how do we index groups to implement this model? Take a close look here. So the upper vector U is an observation on each one of the 8 studies that I'm using in this example. And our data are shown this way. They're shown in a tidy form. So we're looking at the head, the first 6 rows of our data. And in this case, we've just got an X variable, a predictor variable, or a covariate, and a Y. The group number is shown in the group column, and the row number is shown in I. So I goes from 1 to the total number of observations. Now notice the group number changes as we go down the rows. This is the only sensible way to store our data. But this form of the mathematics of the model, IJ, would imply that they're stored in rows and columns. So they're J columns and I rows. That doesn't, I indexes rows and J indexes columns. That's not a sensible way to store your data. So if we store it this way, how can we code to respect the fact that we have this tidy long version of our data file? Well, here's how we do it. We use a little trick that's shown down. Let's go down to the 4 structure that's going to loop over the length of Y. So that's over all of the rows in Ys. And look what we've done with alpha. We have alpha, and then within that, we have a double bracket group I, where group is given as data for each row. And so what that does is that evaluates, let's say for the first 6 observations, that would evaluate group 1, 1, 1, 1, 1, all through all 6. And then the corresponding xi, the covariate, is simply the covariate on that row. So this is really important to know how to do this. If you don't understand this indexing trick, it's very, very difficult to implement these models efficiently. So here's some dplyr from the tidyverse package on how you make indices. I'll just leave this up to your study. This is, of course, in the notes that are on my GitHub site. So the take-home message from this video is that hierarchical models, also known as multi-level models, give us tremendous power to aggregate information from multiple studies in a statistically reliable way to gain insight across all of the studies. Well, that ties up these videos. I hope you found some useful methods and tools for synthesizing existing data and published findings to gain new insight in ecology. Thanks very much.